Let's dive into this explainer and see how statisticians mathematically predict the unpredictable. To do that, we're going to master the big three probability distributions from Dr. Body's notes. Think of a probability distribution like a map. It shows every possible outcome and its exact chance of happening. First up in our tool belt, the binomial distribution. We use this one exclusively for counting discrete successes. But it's got strict rules. You absolutely need fixed trials, complete independence, and a constant probability. Say we know 29% of people smoke. That makes our constant probability, or p, exactly 0.29. Here's the kicker. Just two parameters, n and p, completely define this entire distribution. Pretty neat, right? It shapeshifts based on p, but variance actually peaks when outcomes are a totally unpredictable 50-50 coin toss. So, what happens when your trial count is massive, but that probability shrinks down to almost nothing? That's where Poisson steps in. It tracks super rare events, like predicting individual car accidents nationwide. With a probability this ridiculously tiny, the binomial formula totally breaks down. Poisson is your perfect tool here. Poisson also has this wildly unique quirk. Both its mean and variance equal one single parameter, lambda. Okay, let's smooth out those gaps. We're moving from discrete counts to continuous measurements with the normal distribution. You've seen this famous bell shape. It's perfectly symmetric, meaning the mean, median, and mode sit dead center. It's entirely governed by mu for its location on the axis and sigma for how wide it spreads. Now for a total exam favorite, the empirical rule. It maps exactly how data falls around that mean. Exactly 68% of your data is going to sit snugly within just one standard deviation of the mean. Expand out to two standard deviations, and boom, you capture a massive 95% of all that data. Go three standard deviations out, you hit 99.7%, covering practically every possible outcome on the entire curve. So, with our statistical tool belt fully loaded, how do we know exactly which distribution to actually use? This cheat sheet summarizes the whole shebang: binomial for counts, Poisson for rare events, and normal for measurements. I'll leave you with this final thought. For continuous data, why is the probability of any exact value 0?